I put this presentation together just to try to give folks a base level understanding of the different packages that are out there in the compressed gas industry, uh, how how gases are stored and transported across the country. So just taking a brief look at what we'll talk about today. Just a very brief skimming of thermodynamics, which is essential in determining what kind of a package you can put certain gases in. A history of the cylinder industry. And I want to get into the different types of cylinders that are out there, then bulk packages, how you store large quantities of these gases, and then just a little bit on valve outlets, deciphering what those designations mean, how those valves are operated, and the different types of valves that are available for cylinders. So a little bit on thermodynamics, everybody's favorite subject. What's on the screen here is a vapor pressure curve, and just showing a couple of different gases that a lot of us deal with, just as examples. So starting at the right here is propane, carbon dioxide, nitrogen, and then hydrogen. And anything to the right of this curve is going to be a gas. Anything to the left is going to be a liquid. So you can see that propane, has is a liquid at a much higher temperature than, say, carbon dioxide or nitrogen or hydrogen. The very cold. So with that, you can ship propane as a liquid at ambient temperatures of 70, 80 degrees, whereas at that same temperature, CO2 is a very high pressure liquid or transitioning to a gas at that temperature. Nitrogen is always going to be a gas, and hydrogen, you're hard pressed to liquefy that. Just as an example, here's a video I took at one point in my career of a liquid helium transfer. So what you see here, this is an uninsulated liquid helium hose. And if I play this, I'm not sure if you can see it, but it's you can see liquid dripping off the bottom of this piece of steel. That's actually liquid oxygen. The helium inside that tube is about negative 150 degrees Fahrenheit, and oxygen will actually liquefy from the air right around negative 300 degrees. So, it's frosted. That's water vapor. That's frozen. But that liquid that you see dripping is actually oxygen. Just something neat that kind of illustrates that how that all comes together. Taking a look closer at propane, here's how. I don't know if most of us fired up the barbecue last weekend, but inside that cylinder is a mixture of liquid and vapor. So let's say the liquid line's here, and you've got vapor above it, and what you're using to feed your grill is the vapor off that cylinder. So that vapor is getting used. Let's say you're starting out at 75 degrees. That vapor is getting used and dropping the pressure in that cylinder. And then that liquid is going to boil to replace that vapor to try to bring the pressure back up. So if you've ever used your grill for a long time and you see it starting to sweat the tank, that's because the pressure got down below the dew point in the air. Actually, if you use it hard enough, you'll actually see it start to frost because you dropped the temperature of that liquid down below freezing. And once you stop using that propane, that pressure will start to recover as it warms back up again. Another example, I've reversed the scales here. So this is just looking at water in an Instant Pot, something that a lot of us have in our houses. So here you start out at zero psi when you first fill it with water. When you turn that on, you'll heat that water up to 210 degrees where it starts to boil. You'll hear the air all start to hiss out of the valve. At some point around here, that valve will close, and then that pressure will start to rise. They operate around 12 psi typically, so your water will heat up to roughly 245 degrees in that instant pot. Then once you're done cooking, you've got two options. You can either typically let the pressure release itself, which means that you're waiting for it to cool all the way back down to 210, where it gets to 0 psi. Or if you release it instantly, you open that valve, all that steam hisses out, and if you pull the lid off quickly enough, you'll see that liquid's still boiling inside it. It's because it's still up in the 240-degree range. It'll keep boiling until it comes back down to the 212. So cylinders have been around for a good long while. The first cylinders were made in Europe back in the 1810s. First welded cylinders in the U.S. Came around 1890. First seamless cylinders were made in Germany around that same time, and then in the U.S. Seamless cylinders have been made since about 1902. And actually, a good number of those cylinders are still in circulation in the country. I know I've personally seen a couple that came in for requalification from 1910, 1911. They were still perfectly fine cylinders, and they went right back out for continued use. So there's 5 basic types of cylinders. Type 1 is your most common. That's your all metal cylinders. And then you would get into some composites. Type 2 is a composite cylinder that's with a metal liner that's wrapped around the circumference of it. Type 3 has a metal liner, but it's fully wrapped in carbon. Type 4 has a plastic liner, but it's again fully wrapped. And then Type 5 are all composite. I don't believe there's too many Type 5 cylinders out in the world right now. I think that's where a lot of R&D is being done. But I did not get into Type 5s in this presentation. So your Type 1s, probably one of your most common cylinders that you'll see is the seamless steel cylinder. You'll hear these referred to as DOT Type 3s or 3As or 3 AAs. And the difference between the 3 is basically just the composition of the metal that was used. Physically, they look very, very similar, if not the same. They're also made to an ISO spec. They could be made to an ISO 9809-1, 2, or 3. And these are very common in your high pressure applications. Typical pressure ranges for these, they're rated for 1800 to 6000 psi. These are refillable cylinders. These are pretty much a workhorse of the industry, and you'll find a lot of your permanent gases are typically shipped in these. Those would include your nitrogen, oxygen, argon, helium, and hydrogen. You'll also see other lower pressure gases can be shipped in them, but typically they're the high pressure ones. Very similar to the 3s and 3As, but made out of aluminum are the seamless aluminum cylinders. These are made to a DOT 3AL spec or an ISO 7866. Again, these are for high pressure applications of 1800 to 3000 psi, and these are also refillable. These are, because of the properties of aluminum, these are considerably thicker than steel, but they're much lighter. They're commonly used for medical gases, especially small, home medical oxygen, things like that you see in people's houses. High purity gases, aluminum's a little less reactive to some gases than steel is, so you can keep them at a higher purity for longer times. And also carbon dioxide. see a lot of that in aluminum cylinders because carbon dioxide, if there's water in it, will form carbonic acid, which will do some damage and can rust away the inside of a steel cylinder. For lower pressure applications, there are welded cylinders out on the market. These typically go by a DOT 4B, 4BA, 4BW spec, or also the ISO 4706. By low pressure, typically these are less than 500 psi service pressure, with the most common probably being 240, 260 psi specification cylinders. Again, these are refillable cylinders. They can be made out of steel or aluminum, and you see these used very commonly in the propane or the LPG industry. Some cylinders cannot be refilled. These are disposable, one-time use cylinders. Most of them are made to a DOT 39 spec, and you'll see these very commonly in like a helium tank that you pick up at the party store. The fuel cylinders for your LPG torches, camping fuels, and also refrigerants are very commonly shipped in these cylinders for use. There's also lecture bottles, which are very small, high pressure cylinders, typically about 2 inches in diameter, 10, 12 inches long. They got their name because they're very popular with professors and laboratories for demonstrations in classes. They store a very limited quantity of gas, which helps them to comply with fire and building codes. So you don't have to, you'd fall under the limits for sprinklers, say, or something like that. One issue with these is that they are very difficult to dispose of, which is what it's not uncommon to see a pile of them sitting in a fume hood somewhere because the people in the lab took them, used them, and either wasn't sure how to get rid of them or just hasn't gotten rid of them yet. So that's something that you want to certainly avoid if you are using these cylinders. Getting away from the type 1 cylinders into the composite wrapped ones. The first one is the type 2, which is the hoop wrapped cylinder with the metallic liner. And we say hoop wrapped, that just means that it's wrapped around the cylindrical part of the cylinder, but the head and the bottom are left open. These are typically made to an ISO 11119-1 spec. They are roughly 35% lighter than type 1 for a similar pressure rating cylinder. And the applications are basically the same. If you can use a type 1 cylinder, typically use a type 2 as well. Type 3s, again, these are the fully wrapped cylinders with the metallic liners. These are made to an ISO 11119-2 spec. Again, these are lighter even still than the type 1. That extra wrapping gets you a little extra structural stability. You'll see these used commonly for firefighters or EMTs in SCBA, self-contained breathing apparatus use. And type 4s are fully wrapped with a non-metallic liner. These can also be referred to as COPVs, or composite overwrapped pressure vessels. Spec for these construction-wise is the ISO 11119-3. These are much lighter than steel. You don't have to worry about corrosion. And actually, some folks are making these that are translucent, and you're able to see the contents. I know that's one problem with a steel propane cylinder is it's really hard to tell when it's empty. These cylinders actually allow you to see the level of propane in that tank. For those really cold materials that you want to ship as a liquid, they make cryogenic dewars for those. Typical spec for these is the DOT-4L for an ISO 21029. These are double walled. I think you can see in the picture here where it's a stainless steel shell. There's an insulation gap that's vacuum insulated. Then there's another stainless steel inner, and that's where the liquid sits. So by pulling a vacuum on that, vacuum's an excellent insulator. You essentially eliminate there's three modes of heat transfer: convection, conduction, and radiation. What you're doing is you're essentially eliminating the conduction and the convection by pulling a super strong vacuum on the inside there. So all you're left with is just the radiation between the outside of the vessel and the inner.
Jason?
Typically,
Oh,
yes.
sorry.
No,
I was
go
saying
ahead.
we had a question come in, but I think it was something you covered a couple slides ago about the main difference between a disposable cylinder versus a cylinder that can be refilled.
Okay. Just in how they're made.
I just asked
what's
the main difference between them?
Oh, the main difference is the construction. So a refillable cylinder is beefier. It's made for that cycling of pressure, empty, full, empty, full. The disposable cylinders are typically thinner, and they're made to essentially be pressurized once and then disposed of. So it has to do with the structural integrity of the cylinder.
Gotcha. Thank you.
Mm-hmm. No problem. Again, these cylinders typically will hold the contents at a pressure of 100 to 300 psi. These are used for your cryogenic liquids, so nitrogen, oxygen, argon, carbon dioxide, and nitrous oxide are all commonly shipped and handled in these cylinders. Product inside is extremely cold. As an example, liquid nitrogen at 100 psi in one of these vessels is around negative 279 degrees Fahrenheit. If they're left to sit without using the vapor out of them, that you'll have constant losses of the product that's in them, because there's always that little bit of heat leak from the outside into the liquid, and it's constantly boiling. So that relief valve that is on them will open pretty frequently sometimes. So you always need to take that into consideration when you're looking at where to locate one of these. For instance, if you put it in a small enclosed area in nitrogen service and that valve opens, you run the risk of depleting all the oxygen in that area, which would be certainly a hazard for anybody that was to go in there. There are fancy cryogenic dewars as well for hydrogen, typically for helium and hydrogen service, where you're reducing that radiation leak by adding a liquid nitrogen cooled radiation shield to that vessel. So there's actually a separate container that holds liquid nitrogen in these vessels, and that's cooling this shield here. So you've got, let's say, ambient temperature, 70, 80 degrees out here. All that heat leak is coming in, hitting this liquid nitrogen shield at negative 270, 80 degrees, vaporizing that nitrogen so that you're saving the liquid helium or hydrogen that's in the inner vessel. Liquid helium and hydrogen is they're not easy to turn into a liquid. Once they're there, if you want them to stay that way, you certainly don't want to do anything that would cause them to boil off faster than necessary. Another special type of cylinder is for acetylene service. So these are made to a DOT 8 or 8AL specification for the ISO 3807 typically. These are steel cylinders. They are welded, at least the ones used in the US are welded cylinders, and these are refillable. What makes them special is that they are filled with a porous mass. So the typical mass now is it's made out of a calcium silicate. It looks like concrete, but it's very, very porous. It's actually, if you filled it up with water, it's about 92% porous is the typical standard for this. These cylinders were developed back in the 1920s. Older masses that were used were horsehair. Find some with balsa wood in them, or charcoal, or there were any number of things that people made these cylinders out of. And then inside the porous mass is dissolved a solvent. Typically, the solvent is acetone. There's special circumstances where you'll use another one called dimethylformamide. We'll get into that in a second. But basically, the way the system works is you've got the porous mass in the cylinder. In that porous mass, you'll soak it with acetone, and then the acetylene is fed into the cylinder, and that acetylene dissolves into the acetone for safe storage. So acetylene is unique in its properties, or there might be other gases like it, but it's the most common one anyway. Where if you pressurize it too high or you liquefy it, it becomes explosive. This was a way that folks developed to be able to safely ship larger quantities of acetylene than you could otherwise in, say, an empty, hollow cylinder. Looking at the two solvents, just a comparison of the two. Acetone, you've got a higher vapor pressure, which means that as you use the acetylene out of that cylinder, you will tend to draw more of that acetone out of it. It does have a higher acetylene solubility, so you can, for the same weight of solvent, you can carry more acetylene in an acetone cylinder than a DMF. But it is much cheaper. And again, because you are taking more of it out of the cylinder every time, it needs to be replenished every time you fill that cylinder. DMF, on the other hand, has a much lower vapor pressure. That solubility is lower. It costs more, but you can get roughly 50 fills out of each cylinder. DMF is typically used in applications where you don't want to have to replenish that cylinder, the solvent in the cylinder every time, like in trailers or in in bulk bundles of acetylene cylinders. Just a fun acetylene fact. The smallest acetylene cylinders are known as MCs and Bs, which hold a 10 cubic foot or 40 cubic foot of acetylene, respectively. And these were named as such because they were designed originally to light the headlights on cars and buses. So this is just a picture of an old Buick with an acetylene cylinder on the running board to run the power the headlights. Another term you'll hear in the industry in reference to cylinders is asset cylinders. These are larger cylinders that typically have the owner's name embossed on a neck ring that holds the cap. These are most of these are owned by the gas suppliers and rented to their customers, and the owner is the only one that'll take that cylinder back to refill it. This is in comparison to exchange cylinders, which are typically smaller cylinders, less than 80 cubic foot or so. These have a blank neck ring if they have one at all. The customer will go and purchase one of these outright. Most suppliers will take back anyone else's cylinder and offer the customer essentially a trade-in. So they'll take the empty cylinder and then give the customer a full one in return.
Hey, Jason, can I
Yes,
give you a couple more questions that have come
please.
in while you're chatting? Yeah, we've got
Please.
some good engagement. So I've got a question about DOT. Does it have a maximum service life on COPV cylinders? And if so, where would that requirement be found?
It does. I am not the I'm not the best person to be able to answer that. I believe it's 30 years, and I believe that's in the so COPVs in the US are all done by special permit. And I believe that would be in the cylinder manufacturer's special permit.
Okay. All right. And one quickly from another submitter. How do they get acetone or DMF into the cylinders when filling?
So that process is done before the cylinder is filled. So the process for filling an acetylene cylinder is that cylinder is weighed and the temperature and pressure are recorded. The temperature and pressure are compared to a chart, or there's a formula that will tell you how much residual, how much of the weight that's in that cylinder is acetone and how much of it is acetylene. From that calculation, you calculate how much acetone that cylinder is missing, and you pump acetone into it to bring the level back up to where it's supposed to be.
Gotcha.
From
Thank you.
there, the cylinder is filled, and then weighed again to make sure that the proper amount of acetylene was put into that cylinder.
All right. Thank you.
No problem. Transitioning from cylinders into larger modes of transportation. If you take a bunch of high pressure cylinders and put them on a trailer, you get a tube trailer. Essentially, the tubes are just very large cylinders. They're manufactured very similarly. Uh, Services are the same as high pressure cylinders. Two main types of trailers that you'll see on the road are referred to as jumbos, which are the very large tubes, typically 22, 24-inch in diameter and 40-foot long. You'll see these with anywhere from 8 to 10 tubes. There might be a couple super jumbos that are have 10 or maybe up to 12 tubes. And then the small tube trailers are the tubes are typically 9 to 12 inches in diameter. And these can be 40-foot long. A lot of them are only like 24-foot long. You can put more tubes on the smaller ones. Jumbo tube trailers, the number of tubes is typically gas dependent. So that the heavier the gas you're transporting, the fewer tubes you can have on it, just because of the weight restrictions going over the road. Lighter gases like helium or hydrogen, you'll see those trailers with more tubes on. You can also fabricate trailers out of COPVs, and these are becoming more in fashion because of the reduced weight. The carbon overwrapped vessels are lighter than the steel ones, so you can carry more gas, and there's less steel going down the road. There's also special bundles known as multiple element gas containers, or MEGs. These are assemblies of UN cylinders, tubes, or bundles. These include all of the service equipment, and the framework is designed to be shipped intermodally. So these will go, they'll clip into brackets on a rail car, or a trailer that goes over the road, or you can put these on a cargo ship to be transported over the ocean. Some will also refer to these as an ISO skid. For liquefied gases like LPGs, ammonia or dimethyl ether. These you'll typically see in gas trailers, something like this. They hold around 10,000 gallons. It's basically just a very large low pressure cylinder. And you've got your cryogenic trailers would be similar to your 4L cylinders for delivering cryogenic liquids. They're again, these are double walled. There's insulation between the two vessels. And these, just like those 4Ls, if they're in transit too long, they will vent through the safety relief valve. And then for shipping liquids over the ocean, there are ISO containers for those. These, like the MEGs, are designed for multimodal transport, and they're made for liquefied gases, or some of these are also double walled for the cryogenics.
Hey, Jason,
Yes.
we have another question that came in. Can you define what the service equipment includes or entails?
On a MEGC,
Uh,
I can try. It's going to be
okay.
your manifold. I believe sometimes it will include the regulator to step the pressure down before it connects to the user's equipment.
Yeah, they said yes. Your
Okay.
clarifying question. Yeah, that's exactly what they were asking. So,
Okay, perfect.
thank you.
Okay. You'll never see an acetylene trailer that looks like a regular tube trailer or a bulk transport, just because of the issues with transporting acetylene. The way acetylene is transported in bulk is you manifold roughly 200 cylinders together and connect it with manifolds to the end of the trailer. This is the prime example of where you would use DMF as a solvent. This is all those cylinders are filled and emptied together as one unit. Then you've got your small delivery systems. I'm sure we've all seen propane bobtails making deliveries at ours or our neighbors' houses. They're for filling tanks on site that aren't transported back to the vendor for fill. There's also bobtails that will fill liquid nitrogen, liquid argon tanks, and then Christina's going to like the CO2 squirter truck for filling small CO2 systems in places like bars and restaurants. And you've also got small mini micro bulk systems for high pressure cylinders, which are typically set up in 6 or 12 pack configurations. There's others as well. I've seen 15s, I've seen 18. And the acetylene, some vendors will also supply acetylene in 10 or 12 packs, like what's shown here. And this is again where you'll see the DMF used as a solvent. They're basically set up like small mobile acetylene trailer systems for mats. Getting into how you store gases on site. For high pressure gases, this would typically be done in a stationary tube bundle. Typically, these are built to the ASME, or American Society of Mechanical Engineers, specifications. There's no requalification requirements for these, but there are limits on how many times you're allowed to cycle them in their lifetime. If the local jurisdiction will allow, DOT tubes can also be used for this purpose. For liquefied gases, you'll have your ASME bulk pressure vessels, and these can be huge in size. I've seen 30,000 gallon. I believe they make even much larger than that. But their specifications are similar to how you make the bulk transports or the low pressure cylinders. Just these are made to the ASME specifications rather than DOT. Then you'll have your cryogenic bulk tanks, which are ASME pressure vessels. These, like the 4L cylinders and the cryogenic transports, are double walled and insulated in between the two with vacuum. For things like carbon dioxide, there are refrigerated tanks out there. These are ASME pressure vessels. They're insulated, typically with foam. One difference is these have a mechanical refrigeration system that will keep the fluid liquefied. So for CO2, these typically run about 200 psi, and will keep the carbon dioxide at roughly -15 degrees Fahrenheit. One difference between these and the other tanks for cryogenics is these typically you won't have an issue with these with the relief valve opening on these, because the refrigeration system is condensing whatever vaporizes. Transitioning from vessels to valves, just a brief primer on what the valve outlet designations that are in V1 mean. I know sometimes we'll get questions, what's a female thread, what's a male thread, and that's all kind of explained in this lingo here. So that first designation there, the 0.825-14 NGO, that is the thread specification. So those threads are 825 thousandths of an inch in diameter. There's 14 threads per inch. An NGO tells you that it's a national gas outlet or a straight thread. The RH means that it's your typical thread direction. It's a right-handed thread. That's where the typical adage everybody learns is righty tighty, lefty loosey. So that this one follows that example. And then it's an EXT, an external thread. So the threads are on the outside of the valve outlet. Or this is what we would call a male valve. The opposite of this would be the female valve. So this example was a CGA 300. This is a CGA 510. This is what you'll see a lot on a propane cylinder or an acetylene cylinder. So very similar. This one's 885 thousandths of an inch in diameter. Again, 14 threads per inch, straight thread. This one's a left-handed thread. So if you had two that look the same, one was a left hand, one was a right hand, this keeps you from being able to interchange those two. Left-handed is your opposite from normal. So you're gonna turn this one to the left to engage it, to the right to disengage those threads. And this is an internal thread or a female. So the threads are on the inside of that valve. Looking at different valve operators, the most common that you'll see in the industry is a hand wheel. And it's just like it says, you put your hand on top of that valve and open and close it that way. There are also wrench operated valves. These are also known, if you hear somebody refer to a post valve. And again, it's just we're not very inventive in this industry. It's because there's a post on top of the valve that you put a wrench on. These require a wrench to open and close them. You'll see these commonly on medical Ds and Es, some acetylene cylinders, and in some corrosive gas services. There's also valves that are pneumatically operated. These use air or nitrogen pressure to open and close them. Nitrogen or air is applied to this port in the top of the valve, which will open the valve. You remove that pressure, there's a spring inside that will close it. These are used where you need to be able to remotely operate that valve, such as some flammable surfaces, toxics, for corrosive gases, and when that valve or that cylinder is in a spot where you can't get to it. Similarly, there are also solenoid operated valves, which instead of using air or nitrogen, use an electrical signal, typically 12 volts to open and close the valve. So when this coil is energized, the valve will open, you remove power, and a spring will close that valve. These are used a lot in automotive fuel applications, for compressed natural gas or LPG fired engines. In a refrigerant service, or again when you're not able to get to the location of that cylinder valve to operate it manually. There are also lever operated valves. These you'll primarily see on fire extinguishers. You squeeze the two handles together to open the valve, and these are very, very quick opening. So when you want a lot of flow very quickly, that's where these. Looking at the types of valves, and apologize, these are a little bit small, but your basic valves all have some method of sealing. There's two seals in a valve. You've got the seal going between the contents of the cylinder and the outlet, and also between contents of the cylinder and atmosphere through around the stem here. So three types of seals that you'll see between that will stop the gas from coming up through the stem are the pressure seal, the O-ring, and the pack. The pressure seal, you've got this spring up under the hand wheel that's holding pressure on a piece of packing, and that forms a seal, to keep that gas from coming up. O-ring is similar, but instead of a packing and a spring, it's got an O-ring on the stem here. And then the packed valve is again similar, but you've got a gland nut that you can tighten to tighten that packing. As far as the seal to the gas outlet, most of they're very similar in that respect. So again, getting into the pressure seal and the O-ring, these are typically used for atmospheric gases and mixtures. There's no adjustment that can be made. So once they start to leak, you either have to take the valve apart and rebuild it, or replace it. Packed valves are used for a little more severe service, like corrosive gases, acetylene, higher purity grades you'll see in a packed valve. Again, these can be adjusted a little bit, and they've got a lower leak rate than a pressure seal or an O-ring valve. Getting into fancier valves than that are the diaphragm valves. These have a stack of metal diaphragms here that will that form the seal between the cylinder and the atmosphere. So there's a spring that when the hand wheel's open, there's a spring that pushes those diaphragms up and opens the valve. Then the hand wheel is used to push against that spring to close them. You'll see these used a lot in flammable gas service, for toxic gases, and also higher purity applications. These have a much lower leak rate than a packed valve.
Jason, can I pose another question from the
Please.
audience? What types of valve are isolation and relief valves typically in our industry?
For cylinders, the isolation valve would typically be the cylinder valve, and then the relief valve, there's a few different varieties based on the gas service. So most of your higher pressure gases will have some combination of a rupture disc with or without fusible backing on it. In LP service, typically it would be what we call a CG7 or a reclosing, a spring operated, a spring reclosing valve. Acetylene uses a fuse plug, which is just a fusible metal without a backing. There's no rupture disc on those.
Okay.
Is that, does that answer the question?
Probably.
Okay. If not,
I'll
let
keep
me
an
know.
eye. Yeah, I'll watch the
We can
chat.
come back to it.
Yeah.
No problem.
Okay.
And then fancier still than the spring diaphragm valve is the springless. So this, the diaphragms are actually tied. They call this a tied diaphragm because the diaphragms are tied to the spindle. So when the hand wheel's opened and closed, it's actually physically moving those diaphragms itself. These are used for ultra high purity gases because there's the wetted volume, or what's in the gas path here is much smaller than the other types, and even the where the spring type diaphragm had a spring here that was in the wetted path. The tied diaphragm doesn't have any of that. Something else you'll hear in the industry is about a Viper, or a valve integrated pressure regulator. These are fancy valves that combine all the best attributes of a cylinder valve and a regulator into one piece. These have separate fill and use ports. So at least in this example here, the medical gas, that cylinder is filled through this port, and then you've got the regulated gas port here that a hose would be connected to for that person's use. You'll see these in medical. Again, going back to the home healthcare, you'll see a lot of medical oxygen cylinders fitted with Vipers, and they're becoming more common in industrial uses as well for gases like acetylene. You'll also see some valves have residual pressure valves. What these are basically, it's a little spring-loaded valve that will keep a small amount of pressure in the cylinder as it's used. So there's a spring and a poppet that once the cylinder gets down to, they vary a little bit, but it's about 20 psi. It'll stop the flow of gas so that you can't get any more gas out of that cylinder. These are used to prevent contamination of the cylinder. So if somebody in the field uses that cylinder, doesn't close the valve when they're done, that cylinder will breathe every day with the changes in temperature. You'll end up with moisture and air in that cylinder. This stops that from happening. A hazard associated with these is that you need a special adapter to completely empty the cylinder because you always have that little bit of pressure in them. So before you pull the valve on one of these cylinders, you need to make sure that they are actually empty. But these are enabling longer intervals for requalification in the industry, and it's generally safer. Some places to go for more information on things that I've touched on today. Definitely the handbook of compressed gases, both the online that we put together and is still in progress, but it's getting there. And also, you can find a copy of the printed 5th edition. If you come to the annual meeting, we'll be happy to hand you a copy. V1, which is the standard for compressed gas cylinder valve outlets and inlet connections. V9 is the standard for compressed gas cylinder valves, and V15, which is the use of residual pressure valves. Touching on I didn't get into safeties at all, safety relief valves, but S1.1 is a great reference for that as well, if you're looking for more information on those. So with that, I'll